In this video, I'm going to talk about the one-way analysis of variance, which is a procedure to compare the mean of a response variable, numerical response variable that has a normal distribution among the groups defined by a single categorical variable. We start again, as usual, with the exploratory data analysis to be followed by the frequencies fitting and the Bayesian model fitting. As always, all the codes for these videos, the data and the codes for to run the analysis for these videos are in the site shown in the slide. The general linear model, as we have been discussing, analyzes the effect of a numerical and/or categorical explanatory variable or variables, when there are more than one, on a numerical response variable that has a normal distribution. The one-way ANOVA compares the mean of the response variable, mu of y, among the levels of a single categorical variable, and therefore generalizes the t-test that we had seen in a previous video. And this is therefore another special case of the general linear model. The statistical model could be written as follows. The y is the response variable that has a normal distribution whose mean varies among the j groups, j being the number of levels that ranges between 1 and k. K can be any number, and sigma square this sigma square is the variance of the response variables. In R and in most other statistical software, this model is rewritten as follows. Y is the response variable that has a normal distribution, and we write it in terms of the mean of a reference group plus the differential of the mu alpha sub k, which is the differential of the means between the reference group and all the other means. This reference group in R is taken on an alphabetical criterion, and this can be redefined by using the command ref level. A simple way of depicting this is that we define this, for instance, as a reference group, and this bar here shows the differential, the alpha, showing the difference between the mean of this group and the mean of this second group, and this bar here shows the mean of the reference group and the mean of the third group. Notice that in all of these cases we are assuming that the variable has a normal distribution, only changing the mean its mean values. We can this rewriting of the model allows to focus on the differentials of the means, the alpha sub j's, whose estimation is the main goal of the analysis. Fisher, we will see in a second, partitioned the total variation of y into the explained and unexplained parts. So here we have the variation, the value, each of these values, and here we have y bar bar, which is the mean of the means, the mean of the groups. If we add and subtract the mean of the j group to the right hand side, nothing changes, and this can be shown to correspond to the total variation in the left hand side, and which is equal to the sum of the residual variation, which is the difference between each value and its group mean, and the explained variation, which is the difference between each group mean and the global mean, y bar bar. This can be depicted in a plot as follows. So here we have the distance between the total variation, depicting the 6 hypothetical points, showing the difference between each point and the global mean, the y bar bar. Here we have the difference between each point and its group mean for each of the 3 hypothetical groups here, and here we have the difference between each group mean, depicted as the horizontal lines, and the global mean, depicted as a dashed line. Fisher showed that by dividing this sum of squares by the corresponding degrees of freedoms, he obtained 2 estimators of variance, so from which he calculated their expected value. So he obtained the expected value of the means of square within. This corresponds to the, here was called residual, and this actually corresponds to the population population variance of the response variable. He also calculated the mean of squares between, this is this part, and he showed that this equals to the mean of the response, to the variance of the response variable plus a second term that I'm going to explain in the next slide. So he compared these two estimators of variance as a ratio. He could have compared them in terms of a difference, but he chose to compare them as a ratio. Notice that the numerator, there are common terms in the numerator and denominator, and there is a common positive term, there's a common extra term in the numerator. So if the group means, if the J group means are all equal to each other, they don't differ from the global mean, and therefore the second term is 0, and therefore the ratio of these expected mean squares equals to 1. So when the groups are equal, this statistics f0 equal to 1. When the groups differ from each other and therefore differ from the global mean, this numerator is greater than denominator, and therefore the statistics f0 is greater than 1. The f distribution can be used to assess whether the magnitude of the difference of the means is compatible with the null hypothesis that states that all the means are equal. This distribution was written initially by Fisher and given its name by another American statistician called Snedeker. The shape of the F distribution, its formula is far too complicated and pointless to show in this video. The shape of this F probability distribution is typically this long tail asymmetrical shape as in the red and blue lines, but it can also have this negative exponential shape depending on the values of the degrees of freedom of the numerator and the degrees of freedom of the denominator. When the null hypothesis is rejected, we need to make tests. These tests are called tests a posteriori to detect which group means different from the other group means. So the exploratory data analysis, we start again as usual by importing the data and making and calculating summary, the descriptive statistics. The goal of the analysis is to show whether the daily sleep times of mammals differ according to their diet. Their diet are carnivore, herbivores, insectivores, omnivores, and 7 species for which there was no data of their diet. So the next question is whether these two variables, the numerical response variable sleep total and the categorical explanatory variable diet differ from each other, and the answer is yes, because or at least it appears to be so in this plot, because the medians of each of these groups seem to be different from each other, and as do their means. Notice, however, that for some of these groups there are very few data points, so we should not make too much of a conclusion out of this plot. Although the general linear model assumes that the response variable has a normal distribution, we must always assess it in order to be able to write the likelihood part of the model. This will be done in a second, but first let's calculate the number descriptive statistics of each group using the function desc_stats that was shown in the previous video of this chapter. So we see here that there are obvious differences between the means, especially between the herbivores and the rest, but there are some groups that have very few data points, so we should not make too much of a conclusion out of this meager amount of empirical information. So we obtain the cumulative distribution function and the QQ plots using the package fit_distr+, and we compare two candidate distributions to see which is best to model the response variable. We again use the two candidates are the normal and the log normal, and it seems pretty clear here that the normal distribution is the best candidate that we have at this point to model the uncertainty of the response variable. So the frequencies of model fitting, LM amounts to linear model, response variable, and the explanatory variables. This is the diet. This is where the data is. M3 is the model, and the summary of the fitted model is shown here. Let's recall the statistical model in which we had which was written in terms of the mean of the population mean of the reference group and the differential of means for the jth group, and the variance of the response variable. So first we see the estimated standard deviation, not variance, of the response variable, and then we have a set of coefficients, a set of parameter estimates that I need to explain. What R does to fit this model is that it creates a model matrix, which is shown here, with a set of binary indicator variables that denote that identifies the groups and fits this model as if it were a linear regression. So we had the intercept corresponds to the reference group, which in this case are the carnivores. So this is the mean sleep time of daily sleep time of the carnivores, the standard error of this mean, and the p-value shows that this mean is significantly different from 0, which is of no interest in the context of this problem. Here we have vor herbivore, and this corresponds to the differentials of mean in the mean differential of means between the herbivores and the reference group, the carnivores. This shows that the average sleep time of the herbivore is minus 0.87 hours from the reference group. This is a difference of mean. This is a standard error of a difference of mean, and this tells us whether this difference of means is statistically significant from 0. We have, say, in the other case, also we have for the insectivores, to take a second example, the mean sleep time of the insectivores is 4.56 hours higher than the mean sleep time of the reference group, the carnivores, and this difference of means happens to be, in this case, or is suggested to be, statistically significant, although the p-value is at the margin of the fatidical 0.05 criterion. We also have the R-square, the adjusted R-square, which is pretty low, 0.4%, which is very typical of models that have an explanatory variable that is categorical. So we can also compute the ANOVA table, in which we have the degrees of freedom of the two sources of variation. This is the explained sources of variation, the difference between diets, and this is the residuals, or within group variation, 72. We have the sum of squares, alluded before in several slides before, the mean squares resulting from the ratio between the sum of squares and the degrees of freedom, and the f-value, f0 statistics, corresponding to the ratio between the this mean square 44.6 and 19.9, and this says that the variation, if the null hypothesis were true, we would consider this value to be very close to 1 or close to 1. So the p-value corresponding for these numbers of degrees of freedom is 0.091, suggesting that none of the groups differ significantly from each other. This is the global test of the analysis of variance, called in books as the omnibus test, that tells us whether there is at least one group that differs whose mean differs significantly from the others. So the summary of the M3 shown in the previous slide provided the differential between the group mean of each diet with the reference group, but not of all possible pairwise comparisons of means. In order to do that, we need to make the what is called the a posteriori test, that are explained in greater detail in the book, that allow to compare all group means while correcting for the significance, the correcting the significance level of each comparison so as to keep the family-wise error rate, that is the global error rate of the set of comparisons, as close as possible to 0.05. This is to avoid the multiplicity problem that arises when we make very many comparisons using the same data sets. So the way to do it is to use, one way to do it is to use the package multcomp that allows to making these tests. So the main command is glht, which is General Lineal Hypothesis Test. This is the name of the model, and here we're simply saying that for the categorical explanatory variables we use 2k. 2k here simply means that we are going to ask for all possible pairwise comparisons between the means of the groups, of the 4 groups that we have in our data set. The summary of this, adjusting the p-values for the false discovery rate. This is explained in great detail in the book. So this shows the comparisons, the estimates of the mean difference of some of the groups. So we have the top 3 were the ones that were shown in the summary of the model M3, and so here we have the standard errors of each mean difference of means, the t-value obtained as the ratio between the estimates and the standard error, and the p-values. Now we see that the only groups that are somewhat closer to being significantly different from 0 is the difference between insectivores and herbivores, and this is, well, obviously not statistically significant after adjusting for the false discovery rate. We can also make a plot out of this analysis, which shows again the 95% confidence intervals, the means, the difference of means for each of these groups. So after correcting for the multiplicity effect, no grouping had a statistically significant difference from any other. So in the Bayesian framework, there appears to be no need to carry out this type of a posteriori tests and the corrections. The reasons for that are somewhat abstract, and they are explained in the book. The package Broom gathers the input for the residual analysis. This was discussed in previous videos. We have the response variable, the explanatory variable, the fitted values, the residuals, the Cook distances, and the standardized residuals. With this we make the plots, the following plots. Here we have the standardized residual against the fitted values. We see 4 clouds of points, one pretty small in terms of the number of points, but none of these clouds of points differ in the magnitude of the scatter in the positive side compared to the negative side. Perhaps there may be a minor difference here. We see in the plot of the residuals against the explanatory variable, the categorical explanatory variables, that the medians do not appear to differ very much from each other, with the possible exception of the insectivores. But let's recall that for insectivores we only have 4 data points. This is the 4 or 5 data points. This is the group here. The residuals more or less seem to be normally distributed, except for the tails, which is a problem, and we have a couple of points perhaps that seem to have an inordinate difference influence on the values of the estimated parameters of this model. So this is barely acceptable. It's not bad, but it's barely acceptable. We can, in order to communicate the results, we can produce a table with the estimates, the parameter estimates of the model and its confidence under confidence intervals, and we can also obtain the conditional curve with the package ggeffects that shows, that it gives us the predicted means of each of the 4 groups, not of the difference, not of the mean of the reference group and the differential of means of the other groups. Here we have simply the means of each of the group and their confidence intervals, with which we make the following plot, showing that the means essentially the means of the sleep time of insectivores do seem to differ from the rest, but the uncertainty due to the very low number of species that have this diet precludes us from declaring statistically significant this difference in means. In terms of the Bayesian model fitting, again we start recalling the statistical model, and let's recall the fundamental equation for the estimation of in Bayesian statistics, which is the posterior distribution of the parameters given the data is proportional to the likelihood times the prior. So here we have this equation becomes the 5 parameters that we have, the mean of the reference group and the 3 differentials, because we have 4 groups, and the variance of the response variable given the data. This is the likelihood, the probability of obtaining the response variable given the values of the parameters, times the priors. These are the priors these are the parameters whose priors we need to identify and provide. So this model has then therefore 5 parameters. Therefore it helps a lot to be able to write the model in order to set the priors. We use the command getPrior by stating the formula of the model and the family Gaussian, saying that the response variable has a normal distribution. We have the weekly informative priors provided by VRMS, the package VRMS. This is for the intercept, meaning the mean of the reference group, and these are the differentials of the herbivores with respect to the reference group, insectivores with respect to the reference group, and omnivores with respect to the reference group, and this corresponds to the default prior for the sigma, not the variance, sigma of the response variable. I defined the following priors using a log normal distribution. We are going to see in a second what that means. For the intercept, normal priors for the coefficients of type B, which means that I am defining these priors for all these differentials, the 3 differentials, and I use again a log normal distribution for the sigma, for the standard deviation of the response variables. This means that we expect the mean sleeping time, the most likely value of the sleeping time, daily sleeping time for the reference group, the carnivores, to be roughly 8 to 9 hours, and we expect longer sleeping times to be more likely than shorter sleeping times. This is what allows us to use the log normal distribution that typically has an asymmetric shape. This says that we expect very small differences in the mean sleeping time of each of these diets, of animals of each of these diets with respect to reference group, and that this other prior shows that we expect small values of the standard deviation of the response variable to be more likely than higher values, and of course this precludes, using this log normal prior precludes obtaining a negative sigma, which is not allowed, of course. The formula for the model is pretty similar to the one that we showed in the previous video of the t-test, and therefore I'm not going to comment further on it. We have the part of the summary related to the parameter estimates. These are the marginal posterior distributions of each of these parameters, showing their means, their standard deviation, which here correspond to standard error, and the 95% credible intervals. Notice that the 95% credible intervals very clearly include as a likely value the value of zero difference between these animals of the sleeping time, the mean sleeping time of animals of each of these diets, and the reference group, the carnivores. And here we also have the sigma, the standard deviation of the response variable. We also have metrics of convergence of the three chains. At least the R hat values suggest that the three chains have converged, and that we have plenty of estimates of statistically independent estimates in each of the retained chains. So let's have a look at the marginal posterior distributions of all the parameters, and we see that the three chains appear to have converged to a common and stationary posterior distribution. The degree of mixings of the chains are excellent. There is no chain got stuck in for a very large number of iterations in any particular set of values. All chains evaluated similar ranges of each of these 5 parameters, and the sample estimates retained in the chains do not seem to have a pretty high autocorrelation, suggesting again that they are roughly independent. The largest value is for some lags, for some chains, for one of the parameters. The rest are very much close to zero. Please notice the range of the autocorrelation that is being depicted in the plots. So I'm going to plot together the posterior and the prior distributions to see if the data provided some information that refined our previous knowledge of these 5 parameter values. So in a continuous line we have the priors implied before, and in dotted lines or dashed lines we have the posterior distributions. It doesn't matter the probability densities. What matters in this depiction is the range of values that have support after including information in this analysis. So I again stress that this is the prior distribution before seeing the data, and this is the posterior distribution that incorporates 2 sources of information, the prior and the information in the data. We see that we have substantially refined the mean of the reference group, and more or less the same occurs with the differentials of means between each of these groups and the reference group. And also very dramatically we see the same thing regarding the standard deviation of the response variable. So the difference between the 2 distributions is related to the amount of information in the data that modify the prior distributions. We also obtain the Bayesian R-square, which is pretty low, and it's a 95% credible interval. So this, as I said in the previous video, this is very typical of models that have a single categorical explanatory variable. So in order to assess the goodness of fit of the data, we again obtain the probability distributions of the Pearson residuals and of the fitted values and summarize them in order to obtain the means of the mean of the residual for each of these points, from which we make the following plots, the plots of the residuals against the fitted values. So we again see several discrete clouds, one of which has very small number of points. These are the insectivores, of course, and the rest are more or less reasonable in terms of the magnitude of the scatter in the negative part and the positive part of the residuals. More or less the same can be seen in the box plot showing the residuals against the categorical explanatory variable, in which we see that the medians of the residuals are very similar with the exception of those of the insectivores. But we are not going to pay any attention to that, given that we only have 5 points for this diet. The bulk, but not all the residuals are close to the perfect fit of a normal distribution, except for the information, except for the residuals that are at the tails. So the model seems to have a mediocre, not bad, but mediocre fit to the data. Improvements again is considering another probability distribution to model the response variable, and if possible to add another explanatory variable to it. So to communicate the results, we use the conditional effects commands that allow to obtain the following curve, which contains the means of the posterior distributions for each of these diets and the 95% credible intervals. We can also show the means and 95% credible intervals of the model parameters this time. Here we have of the mean of the reference group, the differentials of the means of the reference group, and the for each of the three diets, and the standard deviation of the response variable. This concludes this video in which I talked about the one-way analysis of variance, another special case of the general linear model. We did the very short explanatory data analysis to be followed by the frequentist and the Bayesian fitting. I hope that you found this video interesting and useful. Thank you very much for your attention.